Once more, as we spoke earlier, that the result for the composition of two functions, one of them is convex or concave, as we spoke previously. All we have to do is to check the following. For the outer function, it should be you should know if it is convex or concave, and also if it is increasing or decreasing. Once more to remember what we mean about increasing functions. While the input increases, the output of this function increases. And for decreasing functions, once the input increases, the value of the function will decrease. Okay? This is what we meant about decreasing, or what we mean by decreasing functions. So first of all, you should check for the outer function that it is either convex or concave. Then, for the outer function, you should be sure about if it is increasing or decreasing. And then look to the inner function, because the composition contains the outer function, as you know, and the inner function, which is the function inside the outer frame. Okay? So, for the inner function, also you should identify if it is convex or concave. Once more, one example to clarify the idea, the example that we explained previously in the previous lecture or in the previous video, but I will go through it once more. So if you look to an E of x, for example, this is the y-axis and that's the x-axis. The shape of E to the power of x, the exponential function, is very, very simple, which is E to the power of x. That's x tends to negative infinity, positive infinity, same for y negative infinity and positive infinity. Remember, that's this function, which is E of x, it's a convex function. So number one, it is convex function. Actually, it's a strict convex function, okay? The second point, it is increasing. Because if you remark, as x increases, increases, you will find also y, okay, increases. So as x increases, y will also increases. So that's the case for the function that we can see from E of x. And the function g of x is also a strict convex function, because this is y. And of course, you know that this is the x-axis to infinity minus infinity, same way like negative infinity and positive infinity, and that's the case for y equal to x squared. So also it's a convex function. If you make the composition f composite g of x, it means e to the power of x squared, which is also a convex function. This is what we mean about this property. So once more, as you can see, for this composition, it's going to be e to the power of x squared, which is a convex function. Why? Because a convex increases function applied to a convex function gives a convex result, as we spoke earlier. I want you also to remember the previous slide, or this table. Just wait a second, I'm sorry. This is the table. Just a second, these all the definitions, we went through it, but I need you to remember this table. This table is very, very important. It summarizes the cases. F is the outer function, remark that, F is the outer function over G of x. And F is convex and increasing, G is convex, so the result will be convex. In a similar manner, if F is convex, but decreasing, and while the G of x, the inner function, is concave, the result will remain convex, as you can see. So this table is important, okay? Very good. And that's the example that we did go through it. To the next property from the some of these properties that's related to convexity, either convex or concave functions, we will speak about the tangent planes polar function. This is very, very important, and that definition is important. Since that if a function is differentiable, so you have a condition that your function is differentiable. Number two, and convex and the f is convex also, the tangent plan to the graph of f are blue or at the same level at the graph of f. It makes sense because if you have a convex, we are stating the case of a convex function. That's a bowl, that's a convex shape. If you have a plane, a tangent to it, this is gonna be the case. So all the points on the convexity will be above this plane. Whatever you move the plane is, all the points will be above this plane, tangent plane, except of course at the tangency point. Do you read me? Okay, does it make sense? Okay. And the convexity, okay, is strict. The tangent planes to the graph of f are blue, the graph of f, with the exception of the tangency point as a told you. Okay, let's look at these shapes. That's a shape of strictly convex curve. Look to the tangent plane, it is actually touching it in one point, and all the rest of the points here are below the graph. Even though if you move your tangent plane to one of the sides, move it as it is, also you will find that the points on the graph are below the tangent plane. Okay? And also that's another case if you move your tangent plane to the side. So okay, what's the equation of the tangent plane? The equation of tangent plane is very, very simple, but you have to memorize it also. It states that for z, which stands for the equation of the tangent plane, it will equal the function at a specific point, which is the point of tangency. Okay, because a tangent plane will touch any shape in just a simple point. So z will equal to g of a and b plus get the gradient vector of the curve. Whatever the curve is, get the gradient vector of the curve. Once you substitute by a and b, you will get the normal point of that plane regarding this curve. Then multiply it by the general vector, which is xy minus a times b. So once more, in order to get a tangent plane, all I have to do, once more, this is z, the equation of the plane, which is now equal to the value of the function at a and b, then add on them the gradient vector of this function. Do you remember how to get the gradient vector? Just differentiate the equation with respect to its variables. So if I have an equation in x or y, what's going to be the gradient? Partial f, partial x. Partial f, partial y. If I have an equation in 3D, x, y, and z, so the gradient will be partial f, partial x, partial f, partial y, partial f, partial z. Then I will do a dot product between this guy and a position vector, which is x and y minus the tangency point. So actually, this equation can be written in another form. Just let them a second. Just let them a second. Stay with me. I can rewrite it in this shape. See, I can say that z will equal to g of an AB plus, if I'm talking about two dimension, so it's gonna be partial g partial x times x minus a plus partial g partial y times y minus b. All I did is just making a dot product. If you remember the dot product between two vectors, we multiply the x component and the x component plus the y component and the y component. Do you read me? This is exactly what happens. Here is the gradient vector, so x minus a will be multiplied in the derivative with respect to x. And for the derivative with respect to y, also will be multiplied in y minus b, as you can see. So this is mainly the equation of the tangent. As I told you, that's the derivative with respect to x times x minus a, derivative with respect to y times y minus b, and that goes for every point. So if you read the definition for which is explaining the convexity of a certain function, so all the values of this function will be greater than the points on the tangent plane. This is what explained. But in mathematics, or an equation form, in the inequality form. Do you read me? Okay, very good. The convex or concave and the tangent function, okay, here's in case of having any two dimension, it's going to be the same, but it's not going to be a plan. It's going to be just simple, a straight line, and the straight line tangent is going to be f at c, which is the tangency point, plus f dash c times x minus c, and that's the generalization of this rule, and it is also explained in this simple graph. If you remark, if you remark this, we are talking in y as a function in x, not as a plan issue, but in just for a function y as a function of x. So see, this is y as a function of x. That's the tangent line, which is corresponding to the tangent plane in 3 dimension. Okay. So in 2 dimension, I'm talking about straight line. In 3 dimension, it will be a plane. Okay. So if you remark, it would make very much sense that all the points on the tangent line will be above the equation of the curve. Okay. And it's coming also straight as a straightforward result from the definition. So here's not just only one plot, the tangent at every point, and they have the same property because all the tangent lines at any point, it will be greater than the value of the function, as you can see. Now the convex and the concave function summarization. This part, I have tried to sum up all the 6 properties that we explained, actually the 5 till the time being. The 6, I will go through it deeply, but after these summarizations. So we summarized everything in these couple of lines. The first property states that, first of all, this is strictly convex, this is convex, strictly concave, and that's concave. So if we are talking about linearity, which means the function is concave and convex at the same time. If your function is concave and convex at the same time, this is what we mean about linearity. Okay, if I have 2 functions, okay, and we added them together, if they are strictly convex, so the result will be strictly convex. If they are convex, the result will be convex, and so on. So it will keep the same property from addition. In the case of product by a number, you already remember this one, once you came, okay? Multiplying by a number, all what's going to happen is between either increasing the convexity or decreasing the phenomena from convexity or concavity, or it will reverse it if you are multiplying in a negative number, right? Okay. In composition, we just spoke about composition briefly, and it summarizes like this. If you have h, which is the outer function, and it is convex and increasing, and the inner function is strictly convex or convex, then the result overall will be a convex function. And you have the table summarizing all of this. The last one, or the last property, it's about the tangency. And for the tangent plan, these are the cases with regard to a tangent equation. If you remember the tangent equation, it's the value of the function plus the gradient vector time the composition or the position vector, which is x minus c. This value, remark, in case of a strictly convex, this inequality or this value should be less than the tangent, or the tangent value should be less than f of x. That's the meaning of these symbols. Do you read me? تاني، أنا مش واضح إنك فاهمين. تاني، دي معادلة بتاعت مين؟ تانجنت بلان. لو أنا بتكلم على strictly convex يبقى الإيكويشن دي هتبقى less than البوينتس بتاعت الاف اوف اكس. طيب لو أنا بتكلم على convex بس هتبقى الإيكويشن بتاعت التانجنت بلان اللي احنا كتبناها من شوية دي less than or equal التانجنت بلان. Do you read me؟ طيب لو أنا بتكلم على concave, strictly concave case, هتبقى equation بتاعت التانجنت بلان greater than f of x. طيب لو انا بتكلم على الكيس بتاعت concave, it's going to be greater than or equal. خدت بالك من العلامات؟ قرايتها؟ اوكي بيرفكت. طيب انا بقى هتكلم ان سبيسيفيك على الساين بتاعت الهيسيان ماتريكس. Either the Hessian matrix is positive definite, positive semi-definite, negative definite, negative semi-definite. So before going further through this part, I would deeply recommend that you link the ideas of how to identify a matrix if it is positive definite, it is positive semi-definite, negative definite, negative semi-definite. If you remember, we took this through more than one operation. One of them was defining the eigenvalues and the eigenvalues. And based on the eigenvalues, we can determine if it is positive definite, positive semi-definite, or blah, blah, blah. Also, we took this classification on the case or based on the minors of a matrix, to get all the minors and to look to the sign and to identify if it was which one of this classification. And the third method, if you remember, we will depend on the principal minors in determining the principal minors of a matrix. And based on the sign of these principal minors, we can classify if it is positive definite or positive semi-definite and so on. Okay? So this part should be reviewed. Look, if I have the Hessian matrix, first of all, do you remember the Hessian matrix? What we mean about Hessian matrix? It is the second derivative, partial derivative. And it's very, very simple, this chart. It is very, very simple. All I have to do is to get partial 2 over f, partial x squared, partial 2f, partial x, partial y, partial 2f, partial y, partial x, partial 2f, partial y squared, get the determinant of this matrix, or this is the Hessian matrix. This is the matrix that I will be interested in identifying if it is positive definite, positive semi-definite, and so on. Based on this, we can classify the function f if it was convex, strictly convex, concave, or strictly concave. Okay? So once more, get the Hessian matrix, identify its case based on whatever you want to do, either the eigenvalues, the sign of the principal minors, if you remember the principal minors, okay, and so on. So if you end up having a positive definite, if it was a positive definite, that means f is strictly convex. If it was positive semi-definite, it's going to be a convex. Okay, so it's going to be, if it was negative definite, so it's going to be strictly concave. If it was negative semi-definite, so it's going to come up to a concave case. To sum up this, for any c-squared function, which is differentiable till the second derivative, okay? Okay, for the convex and the concave, the positive semi-definite or the negative semi-definite will stand for these two cases in specific, okay? So these all the cases that we should go through. Okay, here is the concave and convexity details of a Hessian matrix. The Hessian matrix is, as we wrote simply, is hxx, hxy, hyx, and f double y. Based on this, we can identify the case. We also depend on this in determining the case of concavity or convexity from the two dimensions. So if you have like y equal x squared, you usually stand till the second derivative. فاكر لما كنت بجيب maximum ومينيمم؟ مش كنت بجيب الفيرست derivative، بجيب السكند derivative. لو أنا في multi variables, I will do it using the gradients or the Jacobians. بس في التو dimension اللي هي function in one variable كنت بعمل ايه؟ كنت على طول بروح اعمل القانون الاساسي y equal x squared، بعدين اجيب the first derivative واجيب مين؟ second derivative. This is what's gonna happen. بصي y equal to x squared. So the first derivative is gonna be y equal to 2x. The second will be positive 2. which means this function will be for all strictly minimizing problem or a convex problem, okay? Because the sign of f double dash is always positive, okay? And for this guy, which is 2x, it recommends that or states in the positive direction you will have an increasing function, and in the negative direction you will have decreasing function. That's for x. F double dash is greater than 0 for every x. The derivative of f dash x is greater than x. By the way, I don't have to write this one or to know this one because it's logic. F double dash is the derivative of the first derivative. But he wrote it also for you just to check it. So f dash is strictly increasing and the f is a strictly convex function. Also, if you look for y g of x equal x power 4, the graph of x power 4 is exactly like the graph of x power 2, but it will be more flattened in this part, okay? So that's x equal to the power of 4. So once more, if I start the analysis of x to the power of 4, you will get j dash, which is 4x cubed. Once you do the second derivative, so it's gonna come up to 12 over x squared, okay? And for this guy, also it will remain either positive or 0, okay, based on the numbers. So here we go, j double dash is greater than 0 if x doesn't equal to 0, it's equal to 0, once x is equal to 0, so it is also strictly convex function. If we go to 3 dyne, we spoke about the 2-dimension. If we go to the 3 dyne, for example, for an exponential function, x squared plus y squared, or an exponential function of the type x squared plus y squared. If I want to get the Hessian matrix, it's going to be very simple. All I have to do is to get the first derivatives, partial derivatives, partial x, partial y. Then I will do the second partial derivatives also. Then I will form the Hessian matrix. And I will start identifying if it is positive definite, positive semi-definite, and so on. Let's do it together. First of all, I will need to get all the partial derivatives. So start getting the partial derivative with respect to x, which is really simple. The same function will appear times the derivative of the power with relative to x. So it's gonna come up to the first derivative, it's gonna be e to the power x squared plus y squared times derivative x squared, which is 2x. Differentiate once more with respect to y. It's gonna be the same function, but I will differentiate y squared, which is gonna be a 2 over y. Let's differentiate once more. To differentiate once more, it means I will have to identify f double x, fx sub y, and f double y. Start. So differentiating with respect to x, this equation, it is two functions multiplied in each other. So you get the derivative of the first function times the second, plus vice versa. So this is why it's going to be two terms. So differentiating x will leave you with 2e to the power of x squared y squared. Plus differentiating this guy, it will develop the same function times another 2x. So it's going to come up to 4x squared. Similar debate will be for partial 2h, partial y squared. Once you start getting the mixed derivative, which is partial 2h, partial y, partial x, I will go first for this guy, which is the derivative with respect to x. Then I will differentiate with respect to y. So it's going to add up 4 over xy e to the power of x squared y squared. Now to the Hessian matrix. What I have to do is to make a small substitution about each and every part of them. Now, I will replace hx by its value, hf of xy, that's here, and also it's a symmetric matrix, as you know, and that's the derivative of the y squared. Now, start evaluating this or finding about this matrix, or this identity matrix, for the determination if it was a positive definite or not. First of all, can you get me the principal minors for this matrix? The principal minors? It's really very simple. The first principal minor, it will depend on erasing the second row and the second column, erasing these two guys, which is gonna be 4x squared plus 4e to the power of x squared plus y squared. معايا شكل؟ this is very important. يبقى هيديك بس الاليمنت 1 1 ده الفيرست برنسبل ماينر. طيب السكند برنسبل ماينر اجيبه ازاي؟ هعمل evaluation for this 2 by 2 matrix. I will get the multiplication of the principal diagonal minus multiplication of the secondary diagonal. Okay? Evaluating the determinant. Okay, this is what we have, or this is what gamma isn't. Okay, let's take a deep look for this guy. Is it possible to be negative? This component, look at this component. This is the first minor, which is greater than 0. And that's the second principal minor. Is it possible in any manner that this guy is going to be negative? No way. So both of them are greater than 0, which represents the case of positive definite. Once it is positive definite, which means it's a strictly convex function. So this step is very simple. I have the function by itself. I will start taking this function, getting the first derivative, then getting the second derivative, form the Hessian matrix, evaluating the main minors of this Hessian matrix. بعدين بشوف الساين بتاعتهم، بعد كده احدد الكيس. طبعا هنا على طول الكيس زي ما انت شايفه انها على طول بتديني ان السكند ديريفيتيف is greater than 0، يبقى انا عندي الكيس اللي هي strictly convex. خلي بالك من التكنيك بالظبط، الستبس اللي احنا ماشيينها. ماشي؟ Any questions? Any problems؟
لما يجيلي مسألة زي دي كده بالظبط صح؟
ممكن يجيلي مسألة زي دي، طبعا انت فاهم.
ممكن يبقى مسكين؟
لذلك انا قلت لك بصوا ضروري قوي، لان انا مش ضامن الوقت. محتاجكم ضروري قوي تبصوا على البريفيوس اكزامز اللي موجوده على الموبايل بتاعت منتو. اوكي؟ جاست تو فيل الكويستشنز والمانيبيوليشن. بس دي الكيس لو انا بتكلم على الكونفكستي السبيسيفيك. معايا على فكره احنا هناخد النهارده وبكره. احنا النهارده وبكره.
احنا بس بكره عندنا امتحان.
ساكت. طب خليني خلص بقى نشوف مع بعض. عشان لازم نشوف معاك، اذا ما كانش هنخليكم يوم الاربعاء واجيبكم الاربعاء كتير. اوكي. هنا عندي الفانكشن دي which is 1 minus 2x squared minus 3y squared. Also I want to check the type of the convexity related to this function. So I will get to evaluate the Hessian matrix once more. معايا differentiate with respect to x, differentiate with respect to y. If you do the gradient vector, which is the derivative was the first derivative, differentiating with respect to x, this guy is going to be negative 4y. Differentiating with respect to y is going to be negative 6 of y. That's the gradient vector, the first derivative. I will start doing the second derivative. So that's f of x. Differentiate once more to get f double x. This is f of y. Differentiate once more to get f double of y. And any one of them start differentiating with the mixed derivative. Here's what we have. Differentiating negative 4x once more, it will develop negative 4. Differentiating x with respect to y will be 0. Differentiating y with respect to x will also be 0. Differentiating negative 6y, the first derivative with respect to y, to another derivative is going to give you negative 6. Now let's evaluate the minors. The first principal minor will be the first principal minor will be negative 4. The second principal minor will be multiplying negative 4 in times negative 6. If you multiply negative 4 and negative 6, it's going to come up to 24. So the first determinant is negative 4. The second one is 24. Okay? This guy is greater than 0 and that guy is greater than 0, which represents the case of negative definite. This is why it's really very important to review the part with positive definite, negative definite, positive semi-definite. This part is really very important. Okay? Based on this case represent a negative definite case for the Hessian matrix, so the main function is going to be strictly convex function. Okay, I'm sorry, strictly concave function. Okay, here we go. That's the strictly concave functions. Now I will go through study of extreme points of multivariable functions, which is really the main topic of our search. Remember that we are optimizing, okay? And the bottom line of convexity or concavity, it is related to a maximization or a minimization. Of course, if I'm talking about a convex shape, the bottom of this shape or the lowest point is going to be a minimization point, okay? Either local or global. And if I'm talking about this case, okay, which is the concavity of this graph, also same way like, it represents the case of maximization problem, either if it is local or global. You read me? Okay, the main steps, and I inserted this slide because it's the simplest way to study the cases of explaining the maximization or the minimization problem. Also, this slide, it's not its place, but I wanted to give it to you at the time being to help you out as a tool in your hand, if it is possible, to start classifying the type of the maximum point or the maxima of a curve, okay? The first step, in order to get a detailed explanation of this maximization or minimization, first step is to compute the first partial derivatives. So if I have a function and I want to identify, it is maximization, which is relative to convex, okay, strictly convex. Minimization, which is also relative to a convexity, or the study of convexity, okay? If I want to do this, all I have to do, first step, is to compute the first partial derivatives for the function. So if I have the function in x and y, I will get the function partial derivatives with respect to x with respect to y. If I have x, y, and z, I will differentiate with respect to x, with respect to y, with respect to z. Then I will make these partial derivatives equal to 0. Here we go. Find the critical points. How to find the critical points? Taking these equations and putting them equal to 0. Once you put f dash x equal to 0, you are talking about the case of a tangent which is plane, which will happen if you have a convex or a concave point at the crown, okay? This is why we put the first partial derivative equal to 0. Then I will get the second derivatives. From this point, from this step number 2, I will get the critical points, which are the points which are candidates to be a maximum point or to be a maxima or minima for this graph, okay? So this is the second point. Third point, I will get, or third step, I will get the second partial derivatives. From them, I will get the Hessian matrix. Do you remember the Hessian matrix? Okay, after getting the Hessian matrix, get the determinant of the Hessian matrix. Here is the determinant of the Hessian matrix. That's the determinant of the Hessian matrix, which is simply multiplying the components of the principal diagonal minus the components of the secondary diagonal. Are you with me? So it's going to come up to f double x times f double y minus f xy to the power of 2. That's d. Based on the sign of d and the sign of f double x, I will identify the type of this problem. So, if d is greater than 0 and f double x is greater than 0, you will have a local minimum. Okay? Local minimum will happen when you have a strictly convex curve. Okay, if d is greater than 0 and f double x less than 0, you will have a local maximum. And it's going to be a concave curve. Okay, what's going to happen if d is negative? This guy is negative. It's going to be a second point, which is the point of inflection, but in 3 dimensions. Okay, it's the second point. Are you with me, Princess Shah? Okay, if d equal to 0, then the test is inclusive, and we will go through another steps. We will discuss it within the next lecture in details. Okay. Okay. That's an example of some questions regarding this issue. I hope it will look good in this recording because of the shade and the lighting. Hopefully it will be good. At the worst case scenario, if it is not well represented here, or it's not obvious for you, I've sent you the slides just to go through it. I'm not really sure if you close the lights, it's going to be good or not. Better? Okay. Let's close it. Don't be afraid. Okay. So here's the curve. I'm not really sure if the curve is clear for you or not. But this red line is the curve. Can you see it?
Yes.
Okay. This is the line that represents our function. This curve represents non-convex concave, or concave or convex, or strictly convex or strictly concave. If you look to this guy, it represents strictly concave case. What's the difference between concave and convex and strictly concave? Concave and strictly concave. Strictly concave, you don't have points equal to each other. Okay? There is no points equal. This is the case of concave. Strictly concave, you will never have these points. Okay? So you don't have points equal to each other. So in this case, I would recommend choosing a concave shape. Okay, once more, for this guy, does it represent a convex, concave, none of them, or what? If you look to this side, you will find it going up, which represents a convex. If you look to this side, I'm not sure if it is appearing from the right and so on, or the shape, it is going down. So actually this point doesn't represent a concavity or convexity, okay? So it's not convex or concave functions. I want you also to remember something which is very, very important, that all the strictly convex functions are convex functions, and all the strictly concave functions are concave functions. So this shape, once you look at it, and I believe this is much obvious or clear, I'm talking about the shape, than the other two V's or two shapes. As you can see, it can work for concave, and in this direction, convex or strictly convex. So here I choose it is